This video is going to be a more difficult example of a center of mass problem of a rod. In the example before, it was just lambda is equal to kx, and that would imply that at 0 the entire rod, or this section of the rod, would weigh nothing, and this entire section would weigh k times L. I don't know of any rod that could exist where it weighed nothing at one point and then something at the other point. So I created a more real world example where it was kx plus d. So even at the 0 point, it still weighed something. It still had an initial density of d. So let's get into this problem. This one is a lot more difficult than the previous one. So we know that the center of mass is equal to the integral of x dm over the entire mass. Now, for simplicity's sake, I'm just going to multiply both sides by big M so I don't have to keep dividing by m. So the entire mass times the center of mass is equal to the integral from 0 to L of x dm. But this isn't a very convenient variable of integration, so I'm going to have to find dm in terms of dx, a position variable of integration. So we're going to use lambda to find that. We know that lambda is equal to kx plus d. We also know that that's equal to the entire mass of the rod divided by the entire length. And we know that that's also going to be equal to a tiny piece of the mass divided by a tiny section of the length. Now I'm going to solve for dx in terms of dm, or the other way around, solve for dm in terms of dx by multiplying dx on both sides of the equation. So I'm going to find that dm is equal to dx times kx plus d. I'm going to plug this in, oh wait a minute, dx, sorry, not just d. Now I'm going to plug this in for dm up here. I'm going to find that that's going to be the integral from 0 to L of x times kx plus d dx. Now this is a better variable of integration to use because this is a position integral and this variable of integration is a position variable. So if I FOIL out this x to both parts of the stuff that's inside of the parentheses, we get that this turns into the integral from 0 to L of kx squared plus dx dx. This is a different dx than that dx, of course. Now if we evaluate this, it'll turn into kx cubed divided by 3 plus dx squared divided by 2, evaluated from 0 to L, and that turns into kl cubed divided by 3 plus dl squared divided by 2. Now you can't leave your answer in this form, of course, and this isn't even equal to the center of mass. It's equal to the total mass times the center of mass. So the center of mass is equal to that same thing, kl cubed divided by 3 plus dl squared divided by 2. Take all this and divide it by big M. But you still can't leave it in this form because you have the center of mass in terms of the total mass. And we need to change that. So we're going to find the total mass in terms of k and L. So we know that the total mass is equal to the integral from 0 to L of dm. Now we know that dm is also equal to dx times kx plus d, so we're going to set that equal to the integral from 0 to L of kx plus d times dx. And if we evaluate this integral, that turns into kx squared divided by 2 plus dx, evaluated from 0 to L, and that turns into kl squared divided by 2 plus dl. Now if I plug this in for mass, then that turns into this. We find that the center of mass is equal to, there's no elegant way to write this, I just have to write it all out, kl cubed divided by 3 plus dl squared divided by 2, all divided by kl squared divided by 2 plus dl. Now there isn't really much that we can do with this other than cancel out maybe an L on the top and the bottom, and we can pull out an L from the top, so we can write an L out here and take away that and turn that into a 1 and take that off entirely. So in the end you're left with L times KL divided by 3 plus D divided by 2 on the top, and then you multiply on the bottom, KL divided by 2 plus D. Now that's really the only thing that you can do for this. It's not a very elegant equation at all, but technically you would receive full points for this. I know I told you in the previous video that you know, when you have things in terms of K and you have things in terms of other things other than just the length of the rod, you're usually not done. But with this limited information that we have, that's literally all that you can do. If they gave you values for these different variables, you could compute something that makes sense. So I'm just going to create some values. Let's say that in the problem it said that the linear mass density was, let's say K was equal to 2 and D was equal to, say, 15. So K is 2, D is 15, and let's say that the length of the rod was, I don't know, 5. And you wanted to calculate what the center of mass would be for a rod like that. You would have to plug in all these values for this big equation up here. So when you plug it in for L, it would be 5 on the end, and in the denominator that would be what? K times L, that would be 10 divided by 3 plus D, which is 15 divided by 2. And in the denominator we have KL times divided by 2, so KL that would be 10 divided by 2, and that's just 5, and then you add D, which is 15. So when you multiply all this out, I think you get approximately like 2.7. So it's about roughly half of the rod. And that sort of makes sense because when you have an initial density that's really big, like at this point, if the density was 15 and the rod was pretty short, if the rod was only like 5, then at this end, the density at this end, it's going to be what? 2 times 5, which is 10, 10 plus 15. It's going to be 25. It's going to be, you know, more towards this side, but it's going to be still roughly about in the center. So about right here is where you need to balance it. But if you had like a very small value for D and it was a very long rod and a large value of K, then it would shift more and more towards this side. So I hope that helps. That's a more difficult example. Hopefully you won't have to do something like that, but if you do, you know, I have an example for you to review and look at. If you have any suggestions for future videos, leave that in the comments, and if you have any physics problem you would like me to do, then email that to the link in the description. And that's going to do it for this. Thank you.